Okay, my last video was way too long, and you may have missed the point. And we didn't even finish it. So let me summarize it. Summarize the point. So remember that what Jason Lisle said was that we should see population 3 stars. We don't see population 3 stars, and therefore the Big Bang is wrong. And remember, population 3 stars are stars that only have hydrogen, helium, and lithium. And astronomers agree that there were population 3 stars because it takes stars to make elements heavier than lithium, and the Big Bang only makes hydrogen, helium, and lithium, so there has to be a generation of stars that are composed entirely of hydrogen, helium, lithium, and Pop3. And remember, Jason Lisle was correct to say that we've never seen a population 3 star. But of course, he's wrong when he says that we're supposed to see, or we expect to see Pop3 stars, or that the big problem with the Big Bang Theory. Okay, now the reason why we don't see population 3 stars is because they've all died. Alright? Now, the fact that population 3 stars are made entirely of hydrogen, helium, and lithium means that the gas that they form from was composed entirely of hydrogen, helium, and lithium. Okay, now all stars form from, all stars form via the same basic process. You have some dispersed gas, something causes it to be compressed into a compact cloud. The cloud's in hydrostatic equilibrium, where the pressure gradient force, which point outwards, balances the inward gravitational force. Over time, the cloud radiates energy into space, thermal radiation, so its temperature drops. And eventually it drops to the point where gravity can no longer be balanced by pressure, and then it collapses into a star. And there's an exact criteria for when that collapse happens. It's the Jeans criteria. The Jeans mass of a cloud is based on its temperature, mass density, and mean molecular weight. And when the mass of the cloud is greater than the Jeans mass, it collapses into a star. So you start with the Jeans mass much greater than the mass of the cloud, and then over time the Jeans mass drops as the temperature drops until it drops below the mass of the cloud and it collapses. Okay, so the Jeans mass. So it turns out that the main difference between the gas that population 3 stars form from and the gas that stars like in the Milky Way form from is the temperature. Because in the Milky Way you have things like carbon atoms. In the gas in the Milky Way you have carbon atoms, oxygen atoms, CO molecules, and dust grains. And those things can cool a gas to 10 Kelvin. And when the gas is 10 Kelvin, its Jeans mass is 0.477 solar masses if you use the mass density and mean molecular weight that's observed in the Milky Way. And so it also, about 30% of the Jeans mass actually makes it into the star. So a typical star that forms in the Milky Way would have a mass of 0.1 solar masses. And the Pop3 stars, because they don't have carbon, oxygen, CO, and all that stuff, they only have hydrogen atoms, helium atoms, and hydrogen molecules. And so hydrogen atoms and helium atoms can only cool a gas at 10,000 Kelvin. So if you had a gas that was at 10,000 Kelvin and its density and mean molecular weight were the same as in the Milky Way, then that would have a Jeans mass of 17,000 solar masses, and 30% of that is 5,000 solar masses, and that's too high because you can't have stars that massive. So you can't have stars. You can't, if a cloud has a temperature of 10,000 Kelvin and it becomes Jeans unstable, it's going to collapse into a black hole, not a star. But hydrogen molecules can form when the hydrogen atoms come together, and they have rotational and vibrational energy levels that are much more closely spaced than the energy levels of hydrogen and helium atoms, which means that if you remember that the way that a gas cools is you have two atoms collide, one of the atoms goes to a higher energy state and then it drops to the ground state by emitting a photon, and the photon carries away the energy that was in the collision, and it leaves the gas. So this is the process by which a gas loses, radiates. And how well a given atom or molecule can cool a gas depends on its energy level structure. In particular, it depends on the difference between the ground state energy and the first excited state. The reason is that in order for this to happen, if we assume that all atoms are in the ground state before the collision, then for this to happen, the total energy of these colliding atoms has to at least be equal to the energy difference between the ground state and first excited state. Otherwise, they're just going to bounce apart. They're not going to radiate. But if they have an energy greater than the energy difference between the ground state and first excited state, then when they collide, one of them can be collisionally excited to the second excited state or maybe a higher state, and then it can go to the ground state by emitting a photon. And so, if you look at so I drew the energy level diagrams of hydrogen, helium, carbon, CO, and H2. Okay, so hydrogen and helium, you can see that there's huge differences in electron volts. There's huge differences between the ground state and first excited state. So it takes a lot of energy to excite a hydrogen atom from the ground state to the first excited state, and same for helium. And so, you're only going to have a sufficient number of, a non-negligible number of hydrogen atoms moving at 10.2 electron volts if the temperature is greater than 10,000 Kelvin. So hydrogen and helium only cool the gas to 10,000 Kelvin, and you get a Jeans mass that's too high to make stars. But if you can convince the hydrogen atoms to come together to make molecules, then you have the rotational and the vibrational energy levels, and they're much more closely spaced. So the first excited state of a hydrogen molecule is 0.01 electron volts above the ground state, which you can see is much smaller than the spacing between hydrogen and helium energy levels. But actually, because of quantum mechanics, it's actually forbidden to go from the first excited state to the ground state by emitting a photon. That's forbidden by quantum mechanics because of the symmetry of the hydrogen molecule. So, in fact, to have radiative cooling, you actually have to collisionally excite the hydrogen molecule from the ground state to the second excited state, and then it can drop down to the ground state by emitting a photon. But as you can see, the second excited state, the energy is 0.043 electron volts above the ground state. So for hydrogen molecules to participate in radiative cooling, only the hydrogen molecules that are moving with the energies greater than 0.04 electron volts can do this. And that allows the temperature to drop to 200 Kelvin. And that 200 Kelvin has a Jeans mass of 48.5 solar masses, and 30% of that's 14.5 solar masses. So the Jeans mass, the mass of a star that forms from primordial gas, is going to be of order 14.5 solar masses, which is much greater than the stars that form in the Milky Way, because they form from colder gas, and so they have 0.14 solar masses, but much less than if hydrogen and helium atoms were the only thing that could cool the gas. So if you remember, the lifetime of a star goes as the negative 2.5 power of its mass. So as the mass of a star increases, the lifetime decreases. So we explain why we don't see population 3 stars, because Pop 3 stars form from hydrogen and helium gas. The coldest you can get hydrogen and helium gas is 200 Kelvin. The Jeans mass associated with that is 48.5 solar masses. So that would form a star of 14.5 solar masses. And if you plug that into this lifetime formula, you'll find that the lifetime of such a massive star is way less than 13.599 billion years, which is the amount of time that has elapsed between when Pop 3 stars formed and the present. So all the Pop 3 stars have died. All right, I'm just gonna summarize it one more time. Okay, we don't see population 3 stars because they have all died, and they have all died because their masses were much greater than 0.8 solar masses, which is and so their lifetimes were much less than 13.599 billion years, which is the time between when they formed and the present. And the reason why their masses were so high is because the gas that they formed from could only cool to 200 Kelvin, and therefore the tune's mass was much higher than this 0.8 solar masses. And the reason why the gas couldn't cool below 200 Kelvin is because the only species present that could cool the gas were hydrogen atoms, helium atoms, and hydrogen molecules. And because of the huge spacing between the ground state and the first state that you're allowed to, that quantum mechanics lets you transition between, because that spacing is so huge compared to, say, the carbon atoms and CO molecules, which is what the Milky Way has to cool to such low temperatures. Because that spacing is so large, only when the temperature is 200 Kelvin or higher do you actually have enough hydrogen molecules moving fast enough to make this transition. Okay, and so the point is that there's no mystery in the astronomical community for why we don't see population 3 stars. Okay, stational analysis is the big problem with the Big Bang Theory, but it's not. It's a natural consequence of the Big Bang Theory. It's a natural consequence of the fact that the Big Bang only makes hydrogen, helium, and lithium, and the fact that hydrogen and helium are just terrible at cooling a gas compared to the carbon, oxygen, CO, and all that stuff that we have today. All right?